Okay, we're going to continue on here. We got into chapter 14, I believe, and this is the sort of acid and base chapter, the chapter that has a lot of stuff going on in this particular one. So last time we really just got into sort of the beginning of it, and we were talking about acid and bases. So a reminder that acids are really sort of substances that can produce H plus or H3O plus ions in solution. And remember, in sort of acid-base chemistry, as we talked about, H plus and H3O plus are essentially the same thing. They really represent sort of the acid part. Bases are guys, again, that have the ability to produce hydroxide ions in solution. And when we're talking about these two things, we're talking about really, what affects the pH. And as we'll talk about, is really the amount of H plus that's floating around the solution, or really the amount of OH minus that's freely floating in the solution, not attached to anything, and it's sort of their concentrations. A sort of more general definition of acid and bases, and a lot of times the sort of definition that most people sort of think about when they're doing acid and base chemistry is the Bronsted-Lowry definition that we talked about. And in the Bronsted-Lowry definition, an acid is a proton donor. So basically we'll give it away. And a base is a proton acceptor. As we talked about last time, H plus is also referred to as a proton in acid-base chemistry. Again, because it has a proton, an electron, and no neutron. So obviously when it loses its electron, it becomes just the proton at that point. The sort of consequence of the Bronsted-Lowry definition is we get really, when we look at sort of an equation, oftentimes between an acid and a base, we do get sort of things that are related to each other on opposite sides of the arrow. So usually on the left-hand side, always it's just your regular acid and bases. So the acid on the left-hand side has sort of a partner that is made on the right-hand side of the equation, and that is what is known as this conjugate base. While on the left-hand side, our base will have a partner that is known as the conjugate acid in this particular case. The important difference between those two things is sort of what I think we finished up on last time, is that it should only be one H plus difference. So in order for these guys to be partners or pairs, that is the only difference that there should be. And in terms of an acid, because it's going to basically donate that H plus, the conjugate base will have one less H plus when it's all said and done, going towards the conjugate base. And because basically that proton is going from the acid to the base will accept that proton, and that means that the conjugate acid will actually have one more H plus. So the difference between those things is, again, really only that H plus, and that really is why it is, because it is just really one H plus being transferred from the acid to the base at a time. So the partners can only be one H plus. So I think we saw one, for example, that was like H2SO4 and SO4 2 minus. Again, the difference there was two H pluses, and they are not related to each other. The other thing that we also saw towards the end there last time was the idea that there are certain things that really can behave both as an acid or a base, and those things are what are referred to as being amphoteric. And a lot of times, if it's something that has sort of a hydrogen and like a negative charge, those are typically things that can kind of go both ways. It has the ability, because it does have the hydrogen, and really because it has a negative charge there, it has the ability to give away that hydrogen. It also has the ability really to pick up a hydrogen in that case. And again, that's something that can kind of go both ways, which again is what is referred to as being amphoteric. Water, as we looked at, I think here in the last slide we took a peek at, is also an amphoteric substance. And in certain cases, water can act as an acid. In other cases, water can act as a base. And when multiple waters get together, one would act as an acid and one would act as a base in that case. And that's what we see here. So water is acting as an acid, the other one is acting as the base. And again, we do get our acid conjugate base pair, which is essentially what is happening with water. You know, for example, if we put an acid with water here, what's going to happen again is we're going to get that transfer of the H plus from the acid over to water, and that will make H3O plus and Cl minus. And this is why H3O plus and H plus are kind of the same thing. If we don't include water in that, it's really just the strong acid breaking apart, which, as we talked about, you could just do this, and it's basically the exact same reaction. An equation, obviously no water, we get the H plus, including water in sort of the equation. That's how we generate that H3O plus. But if we did put, you know, something like NH3, which is a base, plus some water here, in this case, water would actually donate the H plus over to the NH3, which would make water acting as a base, an acid in this case. And when it does so, make NH4 plus and OH minus. And again, one of the major things that you should look at when you are writing these equations, besides the fact of being able to write these equations correctly, which is really important, is if you're not sure if you're sort of in an acid situation or a base situation, if you write the equation correctly, you could very easily make that determination by simply looking on the product side. And if you see H3O plus or H plus, that is like a acid type situation. If you write the equation correctly and you see hydroxide, that is a big hint that you should be doing some base type work here, and you're really in a sort of basic situation. So sometimes people overlook the idea of the importance of the equations. It is important. You do have to be able to write these things correctly, and it could actually help you again with the calculations, especially as you go further into this chapter. So if you have trouble writing those equations, just don't like skip over and think it's really not important. A, you do have to show the equations, but B, more so for your calculation part, it can be very, very helpful in the calculation part and pointing you in the right direction in case you're not sure. But when we go back to sort of water here, when water reacts with itself, it actually does set up an equilibrium between H plus and OH minus. And because it is sort of a reversible reaction, we can write an equilibrium expression for it. And it would be products over reactants, but obviously in this particular case here, that is a liquid. So as we talked about, we would not include that into our expression. And what we end up getting is an expression which is what is referred to as Kw. And Kw is the basically equilibrium constant for water, or the ionization constant for water. And basically it is what we see here in this box right there. The Kw equals H plus times OH minus, and it has a value of 1 times 10 to the minus 14 at 25 degrees Celsius. So kind of a cautionary note with this, which is not really too cautionary. Probably in most cases, if you need to use the Kw value, this is probably 100% of the time the value that you would use. But really here, as we talked about with equilibrium constant, right, what is the only thing that actually changes the value of it? Temperature. So if you happen to have come across a problem, which sometimes books will do, and they give you this problem where they say, hey, it's at 20 degrees Celsius or it's at 50 degrees Celsius. Technically speaking, the value of Kw would change based on that. So my guess is in most cases, they will either give you that number in the problem or refer you to a table where you can find that number. But in most cases, if it's 25 degrees Celsius or it really doesn't state the temperature, it's probably safe to assume it's 25 degrees Celsius. And like I said, probably 99 times out of 100, you're going to be using, even more than that probably, you're going to be using the 1 times 10 to the minus 14. But just be aware if you do come across a problem. We used to use a book a while back that used to do that a lot, like, give you some of these problems and the temperature was different. And so you want to make sure that you're using the appropriate K value. But like I said, more times, almost close to 100, that is definitely the number that you have. Also, it should be important to know that obviously you always have that number available to you. Again, not always mentioned in a problem. You may need to use it. And how we use it is basically the H plus concentration, is really the acid part, right, of the solution. The OH minus is the base part. And we can rearrange this equation and solve for either one of them. It's basically the same calculation. It is, if you want the H plus concentration, 1 times 10 to the minus 14 divided by OH minus. Or if you want OH minus, again, it is really the exact same calculation, 1 times 10 to the minus 14 divided by the H plus. So if you're given the H plus or OH minus concentration, basically take 1 times 10 to the minus 14 and divide it by what was given to you. This is definitely a situation where we want to make sure we do use our exponent button. Yeah. So when you type these things in, make sure, again, you're using your exponent button, you're punching them correctly. You will very quickly realize if you are not, because kind of the front part of the number will look okay, but the exponent part will be off usually, and that's usually an indication that you're not using your exponent button correctly. So what can we do with these values once we figure out H plus and OH minus? We actually can compare them. So if we see that the H plus concentration equals the OH minus concentration, it basically means that they both will have a value of 1 times 10 to the minus 7 molar, and that would be a neutral solution. If we look at them and compare the two numbers and the H plus concentration is greater than the OH minus concentration, so essentially the acid part is greater than the base part, it would be an acidic solution. And obviously the opposite would be true here. If the OH minus part is larger than the H plus part, then it will be a basic solution when you do it. There is a relationship between H plus and OH minus, which is important. And that relationship basically is as one goes up, the other goes down. So sort of an inverse relationship that occurs. And obviously vice versa. If the H plus goes down, the OH minus goes up. And that makes sense because if you just think about it logically, if the H plus concentration goes down, my solution now has a lot more OH minus in it, and we would expect it probably to be basic, and vice versa. If the OH minus concentration drops a lot, the H plus concentration should start to rise, and it should be more acidic in that case because you got a lot more H pluses floating around in that case. So they really do go opposites of each other. As one goes up, again, that other one goes down. So why don't we give one a try here? What is the concentration of hydroxide in an HCl solution that has a hydrogen concentration of 1.3? Okay, let's take a look. So we got our Kw that we want to use here, which is the concentration of H plus times concentration of OH minus. And obviously, as we've talked about before, you may see in books and stuff, people use obviously H3O plus in place. So either one is the same, is equal to 1 times 10 to the minus 14. In this case, it gave us the hydrogen concentration. So we could solve for the OH minus by taking 1 times 10 to the minus 14 and dividing it by the H plus concentration, which in this case is 1.3. And in this case, we end up with, looks like 7.7 times 10 to the minus 15 molar in this particular case. First off, any questions on the calculation part? Acidic, basic, or neutral? The H plus concentration is much larger, right, at 1.3 than this number here, which means it is acidic. Plus, it's a hydrochloric acid solution, so I would hope it would be acidic. Yeah. So, any questions on that? Don't overlook those easy little things there, right? They're in the problem. Any questions on the calculation or anything? Okay, let's try maybe another one here. Solution of water, particular temperature, has an H plus concentration of 1.2 times 10 to the minus 6. What is the hydroxide concentration? And again, is it acidic, basic, or neutral here? So again, we'll use our Kw. H plus OH minus 1 times 10 to the minus 14 Once again, in this case, we are given the H plus, so we will be solving for OH minus, which again will be 1 times 10 to the minus 14 divided by the number they gave us, 1.2 times 10 to the minus 6. Making sure you're using your exponent button, 1 exponent button negative 14 divided by 1.2 exponent button negative 6, going to yield us a 8.3 times 10 to the minus 9 molar. So this is a concentration here. First off, any questions on the calculation here? Now, if you were not in scientific notation, you know, you might have just zeroed out on your calculator because you ran out of space and just had an 8 at the end, and that happened. So again, that's how we get to the 8.3, because mine was in scientific notation. If not, your calculator again probably just kind of zeroed out there at the end. So is this acidic, basic, or neutral? Is the H plus concentration greater than or less than the OH minus in this case? The H plus concentration is greater than in this case. A reminder that when you look at exponents that are negative, it's actually the smaller number that's the larger, because -6 means we're going 6 places this way, right? -9 means we're going 9 places this way and putting zeros in front of it. So again, a common mistake as well as looking at that. So this again should be acidic in this case. Yeah. Any questions on that calculation there? Okay. All right, so another way that we do measure acidity of a solution is using pH, and the pH scale does run from 0 to 7 to 14, and below 7 to 0 is acidic, above 7 to 14 is basic, and technically speaking, dead on 7 is neutral. And the reason for that is what we just talked about a second ago. When we are dead on 7, the H plus concentration and the OH minus concentration is actually 1 times 10 to the minus 7, which actually gives you a pH of exactly 7. So there's no misunderstanding. That is what we will call neutral in this class, 7 on the nose. If it's slightly above 7, slightly below 7, then it's either slightly acidic or slightly basic, depending on which way you're going. 7 is sort of our middle point there. If you go towards 0, you're becoming more acidic. And if you're heading towards 14 there, you're becoming more basic. This is our formula here to calculate the pH. The pH is equal to minus the log of the H plus concentration. Again, same thing as you might see, minus the log of the H3O plus concentration. So same idea. Now, speaking of calculators, depending on your calculator, you do one of two things. If you have a display calculator, you put everything in exactly the way you see it. You do the negative, you do the log button, and you do your concentration. If you have a non-display calculator, this formula and some of the other ones we're going to see, you need to work backwards. You actually need to start with the number or the concentration, then hit log, and then hit negative. So this is display calculator. That's the non-display way of doing it. If you're not sure which one you have, all you have to do is hit log. If it says log on your calculator, congratulations, you have a display calculator. If you hit log and it says error, congratulations, you have a non-display calculator. So that's the way you can figure that out if you need to. Let's talk about a couple of things as well. Obviously, at neutral, the H plus and the OH minus concentration do equal each other, which means, again, we do have a H plus concentration of 1 times 10 to the minus 7, which if you put it into that formula will give you a pH of 7. Again, why it is neutral at that point. If you got, again, a H plus concentration that's larger than OH minus, then you will end up with a pH of less than 7, and vice versa. If you got really an OH minus concentration or H plus concentration that's less than OH minus, you will end up with a basic pH. As the H plus concentration goes down, the pH goes up. And again, that's because in this situation, H plus goes down, which means the OH minus concentration goes up. And that would be moving towards basic as the pH goes up, and vice versa. If the pH goes down, that means the H plus concentration went up and the OH minus concentration went down in that case. Now let's talk about Sig Figs and pH. So your pH value, or a value like pH, should have the same number of decimal places as the concentration value has significant figures. So the number of significant figures in the concentration number is how many decimal places, not significant figures, but how many decimal places your pH type value should have. So for example, if we did a H plus concentration of 1.5 times 10 to the minus 5 molar, calculate the pH to the right number of digits. Okay, so if we put this into our equation, the pH would equal minus the log of 1.5 times 10 to the minus 5. You put that into your calculator, again, making sure you use your exponent button there. This is what I get, 4.823908741. So what should the answer be? Should it be all those digits? That's a good answer. It should not be all those digits, but what should the answer actually be? Should it be 4.8? Should it be 4.82? Should it be 4.823? Or actually 4, I guess. Which one should the answer be? So the rule is the number of significant figures in the concentration, which is this one. So let's start there. How many significant figures are in that number? It is 2. When you have a number in scientific notation, all the numbers before the times 10 part are significant. That is how many decimal places your pH should have, which means it should be this one. 2 significant figures gives me 2 decimal places, not 2 sig figs. So that is the rule. And it's also the rule if you're going backwards, as we'll talk about, if you're going from like pH back to the concentration. If your pH value had 2 decimal places, your concentration number should have 2 significant figures. So we're going from sig figs to decimals, and again, backwards as well. Any questions on that? By the way, that would be acidic, basic, or neutral. Would be acidic, it's less than 7, right? And when you're trying to determine acidity, you should always look at the pH scale, because that is usually the scale everybody has in their head. Should not look at any other value other than really the pH value. Any questions on that there? Now, there are some similar scales to pH, and one such similar scale is actually one that measures pOH. The name really tells you what you need. pH, you need the H plus concentration. pOH means you need the OH minus concentration. It's calculated exactly the same way as pH, basically. You take minus the log of the OH minus concentration. The reason sometimes that is helpful is maybe they give you the OH minus concentration and you really want the pH. So there is a very nice relationship between those two things, which is the pH plus the pOH is equal to 14. So if you wanted the pH of a solution, but you're only given the OH minus concentration, you could very quickly calculate the pOH and then subtract 14, and you got yourself the pH at that point. So it's a nice way, obviously, putting in the earlier equation there that we saw. Now, this is a situation where people do screw up, because they will say, when they are asked a very simple question of, is this solution acidic, basic, or neutral? they will sometimes say it is acidic, and they will then say the same solution is also basic, which should not happen, right? So when you're asked that question, is it acidic, basic, or neutral? There really is only one answer. It's either acidic, either basic, or neutral. The reason that happens is because people will calculate the pH and go, oh, cool, that's above 7, so it's basic. And then they'll calculate the pOH for the same solution and go, oh, cool, that's less than 7, so it's acidic. Before you know it, they said it's like acidic and basic, the same solution. So you should only look at the pH value here again to look at whether or not it's acidic, basic, or neutral. The reason for that is, again, that's the one people have in their head. The pOH scale actually runs opposite. So if you have a high pH, you actually have a low pOH, and vice versa. If you have a low pH, you have a high pOH. So they're actually opposite of each other. I've never seen anybody go acidic, basic, or neutral, which I guess is good. But, you know, it's very common people will give both answers for that question. That obviously is the pH scale that we see over there on the left. And we see some common things that we would expect. Up there on top is sodium hydroxide, which obviously is a strong base. A lot of cleaners, as we talked about, ammonia, household cleaners are also obviously basic as well. We see pure water, which is 7. Then we see some acids there on the bottom, vinegar, lemon juice, stomach acid, and some HCl. Now, if you don't have pure water, but you have water that's maybe sitting out for a bit, will it still be a pH of 7? The answer is no, it probably will not be. People are sometimes surprised. Usually it'll be, you know, in that like 5-ish range. And that's because when you leave water out, it actually picks up some carbon dioxide from the air, creates a little carbonic acid, increases the H+ concentration, and brings down the pH of water. So people are sometimes surprised when they stick a pH meter in there and go, whoa, it's like it's kind of acidic. My water here is not really neutral as I would expect. One way, obviously, that we can measure the pH of a solution is right there, the good old original Beckman pH meter there. And that is a pH meter. It's basically an electrode. And when you put it into the solution, obviously, it will give you a direct measurement of the pH after you calibrate it. Really, it works by voltages and stuff like that. So you have some standards that you call pH 7, pH 10, and pH 4, which we'll do when we get into those experiments a little bit later. And it measures the voltages, and then it makes sort of a graph. So then when you put it in your solution, it's got a matching voltage. So it's like a pH of 7 or a pH of 4 and gives you the actual number. Other ways we can measure pH, obviously, is you can use something like pH paper. And maybe if you have a pool or something like that, you get those little test strips, right? You put it in the water and it like changes color, and you kind of match up the color. And that's kind of like how pH paper works. You dip it in the solution, changes color. They have like a little scale, and you kind of try to match up the best you can to it. A couple other important equations why we're talking about it here is if you are given the pH, you could get the H+ concentration directly from the pH, and you do that by taking the inverse log of the minus pH. Now, most people's calculators, when you hit inverse log, it usually will pop up like a 10 and a caret, and you go make sure it's negative of the pH. To do that, typically you hit the button top left corner of your calculator, the second button, the shift button, and the log button. Some calculators have a dedicated button for that, but most you got to do off the log button. You could also do a similar calculation here for pOH. Obviously, from the pOH, we can directly calculate the OH minus concentration, which again is basically the same calculation. It's the inverse log of the minus pOH, which again will usually look like a 10 and a caret. pOH. This is also how most people, or a lot of people, do scientific notation in their calculator, which is definitely why you don't want to do it in this chapter, because you will get the wrong answer as you go through it. So that with our KW that we saw earlier are a lot of the equations that are very helpful here in acid-base chemistry. It also gives you really a variety of ways you could solve some of these problems. You may not even have to use KW. And you could just use, the equations on the right, or you could still use KW. So no matter which way you choose, it all should end up really the same answer with rounding. It should be fairly close to each other, but there are some different ways, obviously, you get to the answer depending on which sort of path you choose there. Any questions on any of those there? All right, let us try some here. let's do on the first one here, the pH on a rainy day is 4.82. What is the H plus concentration? Why don't we add to it? What is the OH minus concentration? What is the pOH? And is it acidic, basic, or neutral? And for the one on the bottom here, let's do what is the H plus concentration as well? What is the pOH? And also, is it acidic, basic, or neutral? All right. So take a few minutes here and work that out for each of those. Pretty much calculate everything. H plus, OH minus, pH, pOH, and is it acidic, basic, or neutral? Make sure your calculators work. pH, which is 4.82. And really from that, you can get one or two information right off the bat. You can get the H plus concentration like the question asks right off the bat. You could also get the pOH by subtracting 14. So we'll start with just getting the pOH here since we're solving for everything. pOH here would be 14 minus our pH, which is 4.82. That would give us a pOH of, looks like 9.18. At this point, and as well, you could have just opened up with getting the H plus concentration. So the H plus concentration is equal to the inverse log of the minus pH. And that would then be the inverse log of the minus 4.82. And that would get you again on your calculator, probably like a 10 and a caret. And make sure you make it negative 4.82. Going to get us a H plus concentration of 1.5 times 10 to the minus 5. It does need molarity at the end since it is a concentration. First off, any questions on those two calculations? We do see 4.82 has 2 decimal places. So again, ended up with 2 significant figures here on our concentration value. At this point, it does open up an alternative pathway as well. We could go back to KW if we wanted to get the OH minus, or we could just now use our pOH that we calculated. So I'm just going to do that way. So our OH minus would be the inverse log of the minus pOH, which is 9.18. And that would get us minus 9.18. Looks like 6.6 times 10 to the minus 10 molar. So we got our pH, we got our pOH, we got our OH minus concentration and our H plus concentration. And is this acidic, basic, or neutral? This is going to be acidic based off of the pH value here, will be acidic. Hence the acid rain, they used to call those things, yes. Any question on any of those calculations? Yeah. Say it one more time, Wesden. So that's the formula to calculate the, so this is part of the formula when you have the pH or the pOH, you're going to get the H plus or OH minus is the inverse log of the minus or negative value, basically. Other questions on that? Okay, looking on the bottom one here, we have the OH minus concentration. So again, we can get the pOH directly from that if we wanted to. pOH would be minus the log of the OH minus concentration, which would be minus the log 2.5 times 10 to the minus 7. That would get us a pOH of 2.5 minus 7. Looks like a 6.60 as our pOH. We can then very quickly get to the pH because the pH should be 14 minus the pOH, which would be 6.60. So plus a 14 gives us a pH of 7.40. And at this point, we need the H plus concentration. And for old time's sake, I will use KW in this case. Why not? H plus is equal to 1 times 10 to the minus 14 divided by 2.5 times 10 to the minus 7. And that would get us what was the last zero? It looks like 4. It looks like times 10 to the minus 8 molar in this case. Obviously, as well. Yes, question? Yeah. Are you talking about these guys here? Or yeah, these guys here, you wouldn't, again here, the concentration that we were given had 2 significant figures, which means we should have 2 decimal places, if that's what you're asking. Yeah. Yeah. No, it's not. It's significant figures to decimal places. So it's the significant figures and the concentration value to decimal places in like the pH or POH. And then it's kind of opposite, going the opposite way. If you decimal places from pH to POH to significant figures and stuff. Yeah. Yep. Other questions on it? And again, like I said, you could get the same value there for the H plus if you just sort of did the inverse log like we were talking about there, then minus 7.4. Again, on mine, I got like 3.98, which if you round up is about 4. So again, with a little bit of rounding differences, you might get a slightly different number depending on which one you kind of choose, but they definitely should be pretty darn close to each other. The difference should probably just be a little bit of rounding depending. Any questions? Oh, by the way, this is acidic, basic, or neutral, this guy. This one is, we would want to look at the pH, which is slightly above 7, which means it is slightly basic here. Any questions on any of those calculations there? All right, let's try one more here just to make sure. Okay, here. So in this case, we are given the H plus concentration. So since we're going to calculate everything, I'm just going to go into the pH equation at this point. Minus the log of the H plus. That gives me minus the log of 3.5 times 10 to the minus 6. And that gets me minus 6. Looks like a 5.46 here as our pH. Again, 2 significant figures, 2 decimal places there on our value. Now that I got that, I can very easily find the POH, which is basically 14 minus the pH. And that would give me 14 minus 5.46. And minus a 14 there. Looks like 8.54 would be our POH. And what is left looks like the OH minus concentration. So now that I have my POH, I could do the OH minus concentration is the inverse log of the minus POH. Again, when you hit that on your calculator, probably a 10 and a caret pop up, 8.54, making sure it's negative. And if I do that here, looks like a 2.9 times 10 to the minus 9 molar, since it is a concentration, needs a value. And that means that this guy is acidic, basic, or neutral. It is acidic, looking at the pH. Yeah, pH there is less than 7, so it would be acidic. Any question on any of those calculations there? And again, as we went backwards here, 2 decimal places to 2 significant figures in our sort of concentration going backwards as well. Yeah. Sorry, I missed the last part. If you were to use. Okay. So is your question like if you had a concentration like 3 times 10 to the minus 9? Is that what you're asking? 0.0. Okay. And then your answer for pH or something would be. Okay. Oh, I see what you're saying. Gotcha. Yeah, no, you would be fine on that. Yeah. So yeah. Yeah, so that's probably just a difference of rounding. And again, maybe if you used KW, you might have got there too, or something like that. So yeah, no, I wouldn't worry about it. It should be okay. No. Other questions? Okay. So let's talk a little bit about acids and bases in relationship to electrolytes. And perhaps you remember electrolytes. Electrolytes are things that when they go into a solution, they break apart and they produce ions, and they're able to sort of conduct electricity. There are strong electrolytes, which basically 100% break apart into ions. None of it stay together. There are weak electrolytes, which basically mainly stay together but produce a little bit of ions. And there's also non-electrolytes, which dissolve but don't really produce any ions, so they don't conduct electricity. The years ago, used to use a light bulb sort of experiment. They put like the electrodes in with the light bulb, strong electrolyte, light bulb would come off really bright because it's conducting electricity really well. Weak electrolyte, you put it in with the light bulb, the electrodes, it will come on but be super dim, again because there's a lot less ions in solution. And then obviously if you put it into a non-electrolyte solution, no light bulb would go off. So when we talk about strong electrolytes, strong acids are also strong electrolytes. And what that means is that they will 100% break apart. So an example of that, if you dissolve some sodium chloride in water and basically made a sodium chloride solution, in that solution, 100% of what you got floating around are basically the ions. So you got no sodium chloride units still together in that solution. This basically becomes like aqueous, which goes there. And it's all 100% ions, which is why it's really a strong electrolyte. Something like this guy here, which is acetic acid, like vinegar, is actually a weak electrolyte. And what that means is when it's in solution, it's actually the whole thing here is mainly what you got. But in solution, it's still able to break apart a little bit into the ions. So we do produce a little of these guys over here. And because it's able to produce a little of those ions on the other side, it's still considered an electrolyte, but a weak electrolyte. And this is also why it's considered a weak acid as well. It's not producing a lot of H+, but it's still producing some. The way you really can see weak electrolytes or weak acids and weak bases is typically in the arrows. And those are those reversible arrows, and that usually would indicate, again, as we talked about with equilibrium, a forward and reverse direction, where basically it's hanging out on the left-hand side there altogether. So these are a list of some of the strong acids which will 100% dissociate into ions, and you would get H3O plus here, plus some Cl minus, since we have water involved. Again, you would get H3O plus some nitrate, get some H3O plus and some perchlorate here, and some H3O plus and really like HSO4 minus. We'll do that. So in solution, this is 100% what we got on the right-hand side, what you have in there. You no longer in solution have any hydrochloric acid guys together or nitric acid guys together. They 100% break apart. So there's like a list of some strong acids, which are helpful to know, and that is pretty much most of them. Hydrochloric acid, nitric acid, that's perchloric acid, that is sulfuric acid, hydrobromic acid, hydroiodic acid. These are all, really strong acids. So if you're dealing with any of these guys, you would expect it to 100% dissociate. And the reason they're really strong acids is because everybody here on the right-hand side is pretty much what you have in solution. So as soon as they go for a swim, any one of these guys are just going to generate a lot of free H+ in that solution, and we're going to see it become really acidic, and that's why they're considered strong acids, because all they pretty much need to do is go in for a swim, and you got a ton of H+ all over the place, and the pH would go down a lot because the H+ concentration went up. And that's obviously different than some weak acids, like some of these here. HF, which is hydrofluoric acid, is a weak acid. HNO2 is nitrous acid. and water as well. So again, you get kind of a similar reaction here. You get H3O plus some F minus. You'll get some H3O plus some NO2 minus. Get a little H3O plus some SO4 2 minus. Yes, sir.
Are these specific acids something we should memorize, or are we allowed to just look at the arrows?
Yeah, well, so if you have the equation, it would be helpful to see it. But in a lot of problems that we use these things with, they don't give you the equations. Yeah, so you do need to sort of know the strong versus the weak, and the best way to probably do that is just to remember the strong acid, those ones I just wrote on the other page. And if it's not one of those, it's probably a fairly good chance it's a weak acid. There is other ways you could determine if something's a weak acid. We're going to talk about a little bit later on this chapter, but there's certain values and that you, if you're given in a problem, will automatically tell you it's a weak acid or a weak base, depending on sort of a certain value, a certain K value that's given to you or not given to you, sort of in the problem. So there's sort of a workaround, if you will, if you really don't know them all or any of those type of things, that you most likely could make a pretty educated guess. But the best one to know, like I said, is definitely probably know those strong ones, because by process of elimination, if it's not one of those, you're probably going to be fairly correct, assuming that it's probably going to be on the weak side. Other questions? Then obviously here we have some H3O plus and some OH minus in this particular case. So in this case, and all these guys, what you mainly have in solution is pretty much these guys is mainly what's in solution. And again, you have a little bit of these guys being formed. So since they're still able to form a little bit of H3O plus along the way, they're considered still acids, but much, much weaker acids than something like HCl. Strong bases are also strong electrolytes. And when we talk about sort of strong bases, they typically are the ones that contain hydroxide actually in the formula. So sodium hydroxide, potassium hydroxide, barium hydroxide. If you look at big group 1 and 2 on the periodic table, as we may have talked about, they are the alkaline metals, the alkaline earth metals. And again, alkaline means basic. So pretty much a lot of our strong bases come from group 1 and group 2 on the periodic table. If you kind of look where sodium is really, and then like potassium, hang a right over there to calcium and strontium and barium, kind of coming this way is really those guys with hydroxide are typically your strong bases. But, when you do see hydroxide in the formula, in most cases, it's probably going to be a strong base. So why it's a strong base in solution, 100% of what you got going on is going to be the ions. Again, much like our strong acids, you will not have any sodium and hydroxide units still together when they're in solution. They will completely break apart. And what makes these guys, again, pretty much all strong bases is as soon as they go for a swim, they are producing a bunch of free OH minus in solution. So as soon as these guys go in, you just entered a lot of OH minus into that solution really quickly. OH minus concentration goes up, H plus concentration goes down, pH goes up, towards basic. And again, that's why they're very strong bases. There's also some weak electrolytes, or weak bases that are weak electrolytes. So F minus, for example, is a weak base. It will accept an H plus like a base would, and it is hydrofluoric acid plus hydroxide. So here it's able to produce hydroxide, so it is a base. Same thing here, he's going to accept an H plus and make some nitrous acid. Actually, it makes where it came from, basically. And also here again, making hydroxide, which is why it will be basic. There is a really important relationship between an acid and its sort of partner, if you will, the acid and its conjugate base, or the base and its conjugate acid. And the relationship is an opposite relationship, which is really important to keep in mind later on in this chapter. So if you have a strong base, or a strong acid, we'll start with that, its conjugate base will be relatively weak. So there's sort of that opposite relationship that occurs. If you got a strong base, its conjugate acid will also be relatively weak. So that kind of opposite relationship. If you started out with a weak acid, its conjugate base will be relatively strong. So again, opposite relationship. And lastly, if you had a weak base, its conjugate acid would also be relatively strong. So what do we mean by sort of a relatively strong conjugate acid or conjugate base versus one that's considered sort of a weak acid and base? We were going to talk about a bunch of reactions which are referred to as being hydrolysis reactions, which is a fancy way of saying water's involved. So basically, when you have a weak conjugate base or a weak conjugate acid, because most of these things are obviously aqueous solutions, there's lots of water in there. What that means is those guys that are weak will not continue on and react with water. So they won't continue on and go through what is referred to as a hydrolysis reaction, which is those guys reacting with water. If something is considered sort of a strong conjugate acid or strong conjugate base, what it typically means in a lot of cases is it will actually continue to react with water that's in the solution. And it will continue to react with the water in the solution, and it will affect the overall pH of that solution because it's basically reacting with water. So later on, we're going to talk about salts. That's basically where this kind of comes into play, and what are referred to as hydrolysis reactions, and understanding that relationship of sort of opposite relationship. If something comes from something strong, it's weak. If something comes from something that's weak, it is strong. It's a really important sort of relationship to keep in mind. Any questions on that? H3O plus and OH minus are the strongest really acid and base that you could get in a solution. Here's a table from your book, which might also help you with the sort of strong acids things. And you can see those are really like the ones we just talked about on that page. You know, so again, if you sort of just kind of remember those guys are strong, you know, everybody else is going to be kind of on the weaker side below it. And there's the opposite relationship here. This is like our strongest acid, and this is a relatively weak conjugate base, and vice versa. Weak acid sort of on this end, much stronger base on this end, and those are the partners across the aisle there. So again, a strong acid or a weak acid will either 100% break apart like we have with our strong acid, or pretty much stay together with our weak acid and break apart a little bit. Now, this is important as well for something like pH, because they may not always just give you a generic sort of formula like H plus or OH minus. They may just give you something like HCl and give you a concentration and go, what is the pH? So if they gave us something that is a strong acid, we know that it would 100% break apart into H plus and Cl minus in this particular example. Now, if I knew that the concentration of this guy altogether was 0.1 molar, what would be the concentration of H plus in this case? Do we know how concentration relates to individual ions if we have the whole thing? So you can think of it kind of like stoichiometry. So when we look at HCl, for every one HCl, we get how many H pluses? One. It's basically a 1-to-1 relationship, which means the concentration of H plus in this solution would be 0.1 molar. And when we look at HCl to Cl minus, it's also a 1-to-1 relationship, which means it would be 0.1 molar for that guy. Concentration of ions in solution are not additive, right? 0.1 and 0.1 doesn't equal 0.1, but it's basically the proportion that you have of the ions when it goes in there. In this case, you get it like an equal proportion, which means they're both as much concentrated in each of them. The thing that's important if we wanted to calculate the pH here would be the H plus concentration, right? Because pH is minus the log of the H plus concentration. So sometimes you may be given a strong acid or a strong base, which you need to either figure out what the H plus concentration is or the OH minus concentration if you're dealing with the strong base to get to the POH and then to the pH. By the way, if you're not sure, the real calculation is when we have 0.1 molar HCl, that is 0.1 moles of HCl per liter, right? That's what molarity means. And as we talked about, the HCl there breaks apart into H plus and Cl minus, which means if we did like stoichiometry, 1 mole of HCl in that equation gives us 1 mole of H plus. The moles of HCl cancel. We're basically multiplying by 1 in this case, right? And we end up with 0.1 moles per liter of just H plus. That's the long version of it's a 1-to-1 relationship and you multiply by 1, which means if it's not a 1-to-1 relationship, it's like a 1-to-4 relationship, you multiply by 4, basically. Yeah. So any questions on that? Yeah. Okay. All right, so why don't we try a couple there? What is the pH of 2 times 10 to the minus 3 molar nitric acid and 1.8 times 10 to the minus 2 molar barium hydroxide? These are both strong acids and a strong base. So take a second or two or a few minutes and see what you come up with. Okay, let's take a look. So again, we could recognize hopefully that nitric acid is a strong acid, which means it is going to 100% break apart into H plus and nitrate. Obviously, we're looking for the pH, which is minus the log of the H plus concentration. So really it is the H plus is the important thing here. The whole concentration here is 2 times 10 to the minus 3 molar. Again, you can very quickly just look at this and it is a 1-to-1 relationship, which means that the concentration of H plus will also be 2 times 10 to the minus 3. And that's pretty much all we need on this one to calculate the pH. The pH would be minus the log of 2 times 10 to the minus 3. And that is going to be something minus the log of 2 to the minus 3. And that looks like a pH of 2.7 in this particular case. That is acidic, which is good because that's nitric acid. So I would hope we would end up with a pH that is acidic. If you ended up with a pH that's basic, you probably screwed up somewhere, I'm assuming. Yeah. Any questions on that one there? Looking here at barium hydroxide, again, is a strong base. So when it breaks apart, we do get a barium that has a +2 charge. We do actually get a couple of hydroxides here. Now, in this particular case, we don't have H plus because we're dealing with a base. So we can go the POH route, which is minus the log of the OH minus. And that is really the thing here that's important. So this is 1.8 times 10 to the minus 2 molar. And we are interested in hydroxide. In this case, it's actually a 1-to-2 relationship. So we do need to multiply the concentration here by 2 to get the correct hydroxide concentration. And if you do that, that would be 2 times 1.8 to the minus 2. 0.036 looks like 0.036 molar. Now we have the correct hydroxide concentration. We could go into our POH. Of 0.036, gonna give us a POH. And remember, this is a POH, not a pH. So this is 1.44. So if you happen to have thought this was the pH, this should not make sense to you because, again, that would be an acidic pH. We're obviously dealing with something that's basic. So at this point, we do need to go, we'll go up this way. The pH here would be 14 minus the POH. That's going to give us 14 minus 1.44. And that will get us a 1256, which is definitely a basic pH and obviously does make sense in this case. Any questions on any of those steps there? So again, not always will you be given just a generic, perhaps H plus or OH minus. If you're given something that you could recognize as a strong acid or strong base, you need to make sure you get the correct H plus or OH minus concentration, and then you could go into the pH or POH. If it's something that is a weak acid or weak base, that is what we will talk about next time we are together, perhaps. So we will lay it up here.